Okay, so we are recording now. We are explaining how the training works for deep learning models. And we said that we had a look at the general structure of how that works for simple models in the linear regression notebook about fitting models to data. We had seen how we could define simple models with just one function. For example, here is a definition of a linear model, and then we had defined a fit function by having these three steps. For the whole data, for a number of repetitions given by these epochs parameters, we always make predictions, calculate the loss, and then update the parameters to make new predictions with this loss backwards. And what we were seeing here is the exact same thing. We define a model before, a little bit higher up. This model is much bigger, has lots and lots of parameters, but we can still define it very easily by reading it from a library, from this PyTorch library, the models part, okay? The models module. Here we had also done transfer learning by reading the weights. This means that we are starting with the parameters trained by ImageNet, when obtained when training the ResNet 50 model with ImageNet, okay? And then once we have that model, then we have the exact same structure that we have just seen for the linear regression. We have it here. We first do the same forward pass. We do the predictions. We apply our inputs to the model. And we were saying that there is a hidden thing that we are doing that inside of the GPU, because here we have moved those inputs to the device. The device is the GPU, okay? It can also be the CPU if you want, but then everything will be that much slower. We are also processing the output, because the output is a vector with a probability to belong to each class. And with this, we choose the class that has higher probability. Then we compute that same idea, the loss function. How far are our predictions from the actual data? Okay, and here I'm calling something that I say a criterion. And then we will need a much more complex loss function, in this case 2, before we use the simple least square function. And here we can also define many that are already implemented in PyTorch. And then we do the same thing. We do the same backward step to compute the derivatives of the loss function when applied to the model and generate a new set of parameters. Okay, this is just to build, these last two lines are just to build the pretty graphs that we see later. Okay. Okay, so that is the most important thing. When we train deep learning models, we do the exact same thing that we did for linear regression. Predict, see how far we are, and use that value to generate a new set of parameters by optimizing, by computing the zeros of the gradients of the difference between the loss function and the deep learning model. So all is a bit convoluted, all has quite a lot of details, but in the end, we are doing high school math. We are doing basically modeling as in linear regression, and we are doing optimization as in find the zeros of a function. And AI is not more deep than that in terms of mathematical abstraction. It is complex in the sense that then it has lots of small details, many small details, and I will tell you about some of the small details of LLMs in a second, but it's not higher in terms of abstract complexity, okay? Here we also have the validation function, okay? And basically in validation, I do not do the the computation of the parameters for the next step, okay? Because the validation function, I only compute the difference between my predictions and the loss function. But the validation set is not used to update the parameters of the model. Okay, and this validation function can probably help you define a testing function. Okay, for the training set, I do change the optimizer. I do use the optimizer to change the values of the model. For the validation set, I don't do that. Okay, and here we even fused the two into one single function. Okay, we have, because they have the same structure, we do one function, and if I'm doing training, I do this last part, and if I'm not doing training, I don't. Okay. Okay. And then here you can see some examples of running this whole thing. And probably here are a couple of interesting things. For example, let me hold on a second for the batch definition, but I have put all of the things that we have been using together. So first, here we have again the definition of the model. Okay. We have something technical in between, but basically we have the reading of the ResNet 50 weights and the definition of a ResNet 50 model. If you want to change the model, you have to change these things. Then I create a data set like we defined in the case of project number 3 in task number 1. I break down, in this case randomly, the data set into training and validation. If you remember, this was something that just divided randomly the data that I had into two, let's say, independent data sets, into the two different data sets. They are not independent because they both come from the same exact data set. Okay. What I said before, what I have inside of the training function is not a data set, it's a data loader. Yes, that is true. What works with the GPU is not the data set, it's a data loader. But in order to create a data loader, I just call it and then pass it the data set. Okay. I have to give it the batch size. What is the batch size? The data set is processed inside of the GPU in parallel. Okay. So I stack my data, my matrices, these are all tensors, matrices of higher dimension, and I put them together in groups. And these groups are processed in parallel. So if I want to process 64 at the time, I will define a batch size of 64, like happens here. Okay. That is all that this means. This data loader is just built by taking the data set and saying how much do you want to process at a time. If I make this bigger, then I will need more RAM memory inside of my GPU. If I make this smaller, it will take longer to train, but I will need less memory. By the way, batch size is not an optimization parameter. Contrary to what many LLMs will tell you, this does not affect the result of the training. Or if it affects it, it's in very marginal ways. This is just about speed. Okay. Then I define the device. Okay. Remember, I said two device before when I was saying that I'm moving my inputs to the GPU. The device is defined here. Okay. Then I do a bit of a technical part where I define the optimizer, the loss. Okay. I put my model into the device. Yeah. I'm not stopping a lot on this. This is also important, but not crucial for beginners, but I'm just fine-tuning my model here. I read something that's called the number of features, which is the size of the output of the layer before last, and then I feed those. Sorry, I create a final linear layer, that vector of probabilities. I am defining it here with the output that I want. Okay, and then I just call that optimized model that we have defined. Okay, sorry, to be fully precise, I move my model to the GPU. and then I define the loss function and I give all of those to the final layer. Okay, let's go again. I define my model here, the shape of my model and the initial weights in my model. Define my dataset and break it into training and validation. 0.24 validation. Those datasets, I transform them to data loaders, which are the ones that can live inside of the GPU, and define my device as the GPU. Here, I slightly modify my model because the model that I have read at this moment is the one trained with ImageNet, exactly with ImageNet weights. One problem that it has is that it has as many exits as the ImageNet set has classes. So that's not what I want. What I want to see is how many classes are there in my data set. In this case, in the case of project number 3, it will be 40 something, the number of species possible, okay? And then I define a linear model module, so basically a vector of probabilities, and substitute the final layer in my model, this model FTFC, with that list of probabilities that I have defined here with the right number of classes. And then I fit all of those things. Sorry, I define an optimizer, general one. There are many optimizers. I define a lot on the optimizer. I can define many from PyTorch directly and don't worry too much about this. And then I call the training function, which because I'm doing training and validation in the same function, I'm calling optimize model. And here I have the model, the loss function in criterion, the optimizer, the data loader for training and validation, and the sizes for those models, okay? The device, the GPU, and the number of epochs. And here I can do some training. In this case, I had defined the number of epochs to 5. So here I'm not running it again, but I have some training examples. Okay. So that is how this works. And you can use this code pretty much as it is for the training task, which would be task number 3, if I'm not mistaken, in project number 3. Okay. If you want to change for subsequent tasks how this works, well, for example, if you want to change the model, you come here and define a new one. And that's all you have to change. Okay, sorry, not all you have to change. Maybe, depending on the model you're defining, you also have to change the way in which we update the end of the model, the last layer, the prediction part of the model. So be careful with that. If you define a different ResNet, that will work exactly the same way. If you define another network, maybe you need to change that too, but that's all you need to do. Okay. Okay. And let me go a little bit into the nitty-gritty details because we are finally ready for those. So on the one side, I had this checkerboard classification thing. I'm not running it again. But last week we already saw this beautiful graph where we had trained, and now that we have seen all of those things, if you see here, I have the number of epochs, the data set, the weights, which are written in exactly the same way, the model, which is defined in exactly the same way. So this is the same thing. The data loaders from the data sets in exactly the same way, the same change of the final layer, and this same optimized model function being called here. Okay, so here I'm just recycling the use of the things that we have just seen, and you can do the same. Okay, but here interesting thing was that we got this validation loss to flatten after 4 iterations while the training loss kept going down and down and down. We call that overfitting. And that means that between the two problems that we said we had, one is a theoretical problem of finding the values for the parameters in my model that best predict the training set. That one went perfectly, very nice. And the second model, which is actually doing something practical, in this case, counting number of blue and red squares in these images, or in your case, actually classifying new images, okay, the practical part, which is kind of monitored by the validation set. Well, that one didn't go so well. In terms of accuracy, the training went to 100%, let's say, and the validation accuracy stayed at 0. Here, because my data was not enough, if you remember, what we had done here was define a very small training data set with only 10 images. So essentially, we could see this as the model memorizing the 10 images very, very well, but that meaning nothing for the generalization power of the model. Generalization power is defined as this link between the practical and the theoretical problem. If my model trained on the training set also can be used to solve the practical problem, then we say that my model generalizes. Okay, we had seen that the confusion matrix was horrible, and then we defined a bigger data set with the exact same things, and we got the loss and the training and validation loss to behave, and the confusion matrix to be much better. Okay, so this is a technical way in which we do training. About the way LLMs are trained, I wanted to do a bit of a reflection here using something personal, which I think is always easier to relate to. Let's see. Sorry, before we do that, I don't know if there is any questions about training. I'm sure this is a difficult subject, but I don't know if there are any questions at this moment. If not, you can always ask them later. Not at this moment. Okay. So I wanted to reflect again on the nature of these LLMs, AI assistants that we are all using quite a lot these days. Basically, what's the connection between the ChatGPT that you ask questions to, or I ask questions to, or Gemini, as you're seeing here, and all of this nonsense about linear regression and training images and so on? Well, basically, the way LLMs work is that they receive some text input, and here we have some text input that I gave to Gemini yesterday, and then they start by transforming this text input into numbers, into matrices. Okay, because the first thing that they want to do is have matrices, because all of these deep learning artificial intelligence networks only work with matrices. They do that by a process called tokenization, which means that they transform these into some numerical code and use some predefined matrices to compute some matrices out of the text. Okay, I will not stop in this tokenization thing because it can be very long and it's actually not that interesting. But essentially, it's this process. I could do something like a very simple tokenization. I could assign numerical value to each letter in the alphabet and then make a long numerical list here and then break at whatever length I want and use that as a matrix. So make so many numbers is one row and then so many others is one row. That would be one way of tokenizing. Not a very successful one, but you can think about this kind of thing. So, or I could do that and then multiply for some matrix that someone else has already tested and seen that helps with the translation of text to numbers. Okay, this is something that's well established, and this is the reason why there is these famous examples of LLMs not being able to count the numbers of R's in the word strawberry, for example, because LLMs do not work with language like we do. They are programmed to start by tokenizing and converting the words, the text, into numbers. And they don't have to convert them, let's say, letter by letter. And they definitely do not process the input letter by letter. That's something that we tend to do in our heads. LLMs are not programmed to do that. They work differently. And that's why it's quite difficult for an LLM to count letters or to work directly with letters. Some of you might think, okay, but if now I ask, let's see, Claude, okay, let's say, count the number of R's in a strawberry, I will very likely get a correct answer, okay? There are 3 R's in strawberry, okay? This is correct now. This used to be wrong, okay? Why is this correct now? Does, in this case, Claude work differently to the ChatGPT versions that could not count strawberry? And the answer is that no, Claude actually can still not count the R's in strawberry. But why am I getting the correct answer then? Because of the apron, okay? The apron, or let's say added software on top of the just LLM processing software. When I enter input inside of any LLM, Claude, Gemini, ChatGPT, whatever, it doesn't go directly to the tokenization step and so on. There is a first step where, let's say, annoying queries are filtered. So for example, LLMs also cannot do any math in any way. But if I ask how much is 2 plus 1/3, I will probably get the correct answer too. Okay, see, identified straightforward arithmetic problem. 2 plus 1/3 is 7/3, which equals about 233, or 2 1/3 as a mixed number. This is a pretty good answer, but here we are getting quite a lot of information. And even more, this is a straightforward math problem that doesn't require any context for previous interaction. So this is just old regular if programming probably, where because I said how much is, it was identified that this is actually a math problem, and we have completely bypassed the LLM part, and we have just been connected to a simple stupid calculator with some embellishment with the, let's say, they have done symbolic computation and then floating point arithmetic and whatever, okay? But we have barely touched the artificial intelligence part of the software here. Before all of this apron, all of these extra things, extra layers over the product were not there, and that was why we got this kind of funny replies. But this is not intelligent. So this, what we have gotten here is just an answer from a regular ask calculator after we were directed there by a simple filtering tool, okay? Similarly, my friend, when I used to ask about, how was it, that one, John's mom had a son called had 2 sons. One was named Peter, two children let's not be so bad, had a son named Peter and a daughter named Rachel. Okay, I misspelled. Okay, what is the relation between Peter and John? Okay. And again, here we have been redirected to a logical deduction module. Okay. LLMs with their tokenization and their text prediction capabilities absolutely cannot do this kind of simple relation between Peter and John. This is more or less obvious because of the context, because it's John's mom and Peter is John's mom's son. He's also John's brother. Okay. LLMs left on their own would completely mess up this, and that's why these companies add to this pre-processing step, to this apron, all of these other, let's say, simple capabilities. Again, this is just deduction software based on simple rules, and this can only make these kind of connections. Someone has taken the time of saying, okay, if someone says someone is someone else's mom, then you have to build a tree of relations in this way. This is a whole completely different area of computer science that has nothing to do with artificial intelligence, interesting on its own, which is called automatic reasoning, and which is also very limited in its own way. All of these products are designed to make us feel that we are relating to some kind of intelligent entity, but we are not. We are just being fed lots of text, which always looks pretty and normal and fine and nicely grammatical from all of these LLMs. And then occasionally, when we stray out of the path, we are redirected to these other types of aprons, okay? But that is very problematic because there is no, let's say, fundamental intelligence to any of that. And the different capabilities, the capability to handle numbers or the capability to make pretty text or the capability to reason to derive information from a set of rules defined in a very particular way, those are fundamentally connected by something that's just not intelligent and that's very limited. Okay. And that pops up into any query that you make from these LLMs. This is an example from yesterday. I have a friend who wants to visit Oshima Island near Tokyo, which I have never been to and looks interesting. Okay, for example, I think I can open this here. This is a real thing. This is the PDF, touristic PDF from this island, and it looks pretty cool. It's a volcanic island that you can actually bike around and so on. But the thing is that my friend is not super in good shape, and the whole thing is 46 kilometers, the whole tour of the island. And I was wondering if he had time or not. So I asked Gemini about that. And then it says that the route is approximately 43 to 46, and then it was uh, let's say data mining some of the information in the pages. LLMs can more or less do that, so my friend should budget 5 to 6 hours total, is saying here. Okay, and then it's copying some of the information in the prospect that it's linking here about safety and best loop and so on. And I was asking, but remember, he should budget 5 to 6 hours, okay? And then I knew that the my friend had told me that he had exactly 6 hours in the island, and I was thinking, okay, so he does have time for that. But then I asked the LLM about if he comes in the first ferry and leaves with the last one, does he have time? And then the whole thing completely changed because this again triggered the reasoning part of the apron, and here other things were taken into account that had not been taken into account in the initial part. Okay, so what is triggered and what is not triggered is completely arbitrary, and sometimes it's right and sometimes it's not, and it's very, very difficult that they will ever get it right correctly. Okay. Here, the whole thing changed completely because here the LLM, not the LLM, but the whole software, let's say, brought up the thing that you need some buffer time because you need to actually, my friend needs to rent the bike and fill the paperwork and so on, which I was thinking about. So the total time becomes much more tight and the whole thing becomes much more difficult. Okay, so when the reasoning part has not been triggered, you get one answer. When it has been triggered, you get another. And important point, all of this is false because the information here has not been data mined correctly because LLMs have no way of knowing if the information they're getting is up to date, if they are reading it from the proper page. They just make pretty text. So the hours from the ferries and so on are also incorrect. So all of this is bullshit. LLMs are very useful for making text. They cannot think in any meaningful way. We get lots of effort from companies to make us think that they do think in some ways. They make all of these other models on top of them to convince us. They can be useful sometimes, but you absolutely cannot rely on them because fundamentally they cannot do the things that they are supposed to be doing. Okay. Okay. So that was a little bit about how to train all of these LLMs and how to train deep learning networks in general. I had opened, and I want to finish with this, if I find it again. I had opened a paper by Marco and myself and Professor Lopez too about this practical use of these training and testing things. And this goes for the going deeper task. Okay. I said before, when we used this random sampling and we had a validation set that was essentially the same as the tests, as the training set, just by random subdivision, we ended up with this very, very pretty 96, 98, 98, 97.83 on average accuracy. So number of percentage of correctly classified patches for our problem, which is essentially the same with different data problem that you have for project number 3. Okay. But we are not really interested on that. We want to know if I train my model with one particular set of data that I think is representative of the general problem, and defining representative is not possible. But let's say there was such thing of a representative data set. Let's say I do my best and I try to find a data set that I hope captures the characteristics of the practical problem that I want to solve. And now I use it with different data, with new data, because that's the main point to do practical things. When instead of doing that, we divided our training and testing sets according to site. So all of this data came from different sites. And what we did was that we changed the way of dividing things. Instead of doing just random things, we left out one site as the test site and used the data from the other sites for the training and validation sets. And that would mimic, I have some data sites where I take my data and train my models, and then someone comes with a new data from a different site. In this case, the accuracy, we did that 3 times, leaving different sites as testing sites and the others as training sites. The accuracy was still not horrible. 95, 92, and 83. So here, on average, we had a drop of 7% in accuracy. And this is the kind of practical drop that is interesting to see. When I don't have the exact same distribution of class weights, of class percentages, as happens when I do my random subdivision, if I do it differently and I have more patches, more percentage of patches of one species in the testing set that I used to have in the training set, then my accuracy drops. And it dropped 7%, which is still not terrible. It's 90% accuracy, which is great, but not 98% or almost 98% anymore. This is the drop that you get when you try to estimate the real values. But even more than that, here we also had the F1 score. F1 score, as I said before, is a kind of weighted average between precision and recall. And for our purposes here, the most important part is that this is not weighted by the number of patches in every class. So basically, small classes, classes with very few patches, and classes with lots of patches contribute exactly the same. So if I mess up the small classes, this is going to suffer a lot. When I did my random subdivision, I ended up with 94.99, 95% F1 score. Okay. When I do this more realistic type of testing, my F1 score falls off a cliff. From 92 to 49, from 85 to 68, and from 97 to 37 in the same number of fold, which ends up with an average of 51.77. The picture here is that I get almost perfect accuracy, and I classify even the small classes with 95% success. The picture here is that I more or less can classify the big classes, but not the small ones. Understanding the difference between these training, validation, and testing data sets and choosing them in a way that is realistic, that mimics the conditions where I want to use my models, is the difference between having something that, so the top part, many papers are published just with this type of information that looks great in practice, but is not, let's say, that great for real life use. Okay, and understanding the limitations of the technology and the difference between these data sets and what they mean is something that many people are not able to do. Okay, so next time we will talk a little bit more about testing, and testing is just, sorry, yeah, here, close. In order to not this one, in order to test, yeah, this one, we just need to apply the model. So something similar to the validation function, but the choice of the test function and what test and the test set and what the test result means is an important subject that we will dedicate some time to next week. We have 5 more minutes in case there is any question at this moment. This has been a bit of an intense session, and I hope I gave you some, let's say, food for thought in these different lines. Okay, I don't know if there is any question at this moment. Okay, so let's keep working on this. I would say, absolutely, if you have not done that yet, finish task number 1, and if at all possible, task number 2 by next Monday. Okay, those are very crucial. Task number 3 about training, you can If you have done task number 2, let's say, correctly, you can pretty much leg it with this code that we have been seeing before. But task number 1 can be a little bit annoying, and task number 2 needs just a little bit of fine tuning to read the images that you create in task 1 correctly into a data set. So I would say make sure that you get them going as far as possible. So next Monday you can ask questions, or you can ask me questions during the week. And if by the end of next lesson you have completely nailed tasks number 1 and 2, then 3 is pretty simple, and then you can dedicate the final week to task number 4, which I think is fun, and you can think about all of these considerations. Okay, we have this problem with the notebook that I have made a note of, and I will update you as soon as possible. Okay, so let's finish it here for today. Apologies about the interrupted recording, but I think we still managed to cover most of what is important here, thanks to your memory and not mine. Thank you very much for listening, and see you next time for the last lesson of the course.
Thank you.
Thank you.
Thank you.